So the first lab is graphing techniques. Has anybody, you should have had a little bit of introduction to graphing in math class. Is that true? Yeah. Okay, good. So we're only going to focus on one type of graph, that is using the Cartesian coordinate system, which looks something like this. That's a complete, well, that's incomplete, but it's a beginning for a Cartesian system. This is known as the x-axis. This is the y-axis. This is also called the abscissa. I can remember how to spell that thing. Yeah, I thought so. Abscissa, and this is the ordinate. Okay. So far, I'm only talking math. I'm going to make the transition to science in a second. This is the origin. And any data point that we place on this graph has two values, one x and one y, right? So on this side, all the x values are positive. On this side, all the x values are negative. And similarly, positive values here, negative values here. For the sciences, most of our graphing takes place in this quadrant. There are four quadrants. This positive quadrant. We do, however, sometimes go into this quadrant with data, and occasionally we'll use one of these others, but we're in this class, we're only going to be using this one and this one. Right? So when you draw the graph, you can ignore this part of it down here. Okay. So when we have a data point, what does that data point mean? Well, it says right, where is it? A measurement is, hold on a second. I thought it was right here somewhere. Well, shoot. There it is. Any point on that graph represents an experimental measurement. And it means, based upon this information here, it means that the experimenter has introduced into the experiment an independent variable. The experimenter controls what that variable is. For instance, if I say I establish a temperature in a trapped gas of 50 degrees Celsius, then I measure something, its response to that. So I have controlled the x-axis, the independent variable. That's this axis, independent. So I say 50 degrees here, right? The response is whatever the gas does that I'm measuring. Say it's volume. So I measure the volume of a gas when I make the temperature 50 degrees, and it's up here somewhere, right? So over here is something, let's just make something up. Say it's 10 liters. This is the dependent variable. Okay. So the experimenter controls this. The response is this, and this data point right here represents 50, 10. Okay, X, Y. So how would we label this? Well, this axis would be labeled temperature in degrees C. This one would be labeled volume in liters. So we have to label our graph. Otherwise, we don't know what those numbers mean. So we label this one temperature degrees C and this one volume. This identifies what it's measuring. This identifies the units of measure. Okay. So that data point is has X and Y buried in it. Okay, so if we change the temperature again, right? We change the temperature again, say we decrease the temperature, then we might get something out here. Decrease it again here. So what we're seeing is, as we decrease the temperature, the volume of the gas decreases. And say we only make those measurements. Now, when you're plotting these values on a piece of graph paper, you have to decide several things. One is, how do I get the maximum use of that piece of paper? Right? If you have a piece of paper like this, and you draw your axes in here like that, and all your data points are right here, look at all the space you've wasted. Besides that, with the data points that scrunched together, if you want to go in here and say, well, what if the temperature is not one that I chose, but it's like in between in here, then you want to be able to say, all right, what would the volume be if I chose that temperature? Then if they're all scrunched together, there's no way you're going to be able to do that. So you want to spread out and use the entire page, or as much of it as possible. So you try to spread your data out as much as possible on these axes. Then we've already decided which is independent and which is dependent. Then we want to scale it so it uses as much of the space as possible. So you want your maximum value to be out here somewhere, and your maximum here to be up here somewhere, and then in between you spread the rest out. And when you do that, then you have to choose the units here. Like you've got a grid on the paper. Those are the lines that are drawn on the paper. And then you choose your scale units so that you can get the maximum use out of it, right? In this case, the units are chosen for us, degrees C and liters. But you can also say, what does 1 liter represent? Well, in this case, 1 liter is probably about right there. So that'd be 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you label those grid marks. And 50 degrees here would be like, let's see, 1, 2, like that. This would be 0. In fact, the origin is always 0, 0. So it'd be 10, 20, 30, 40, 50. And then 60, 70, 80, and you could go on out if you decided to increase the temperature further. But if 50 is the highest one, then you want 50 to be way out here. And if 10 is the largest volume, you want 10 to be way up here. So you use the maximum amount. Also, you want to pick the orientation, because a sheet of paper is going to be either in portrait or landscape. If it's in landscape, then X needs the most room. If it's in portrait, then Y needs the most room. All right? Things to consider. Now, once we've put our data points on this page, then we want to to draw a best fit line. This one looks like it's a straight line. So you get yourself a straight edge, preferably a straight edge that you can see through. The reason for that is, suppose, let's see, suppose I had more than 1 point. Say I had one down here, and I had one up here, and I had one over here. So we see some error involved. If you think that's a straight line, then you want to position your straight edge so that you minimize the deviations of the points from that line. That's a best fit line. So without a straight edge, I'm going to estimate maybe like this, something like that. And that would be your best fit. We call it a curve, best fit curve. So if you do have data that tends to curve, then you draw best fit on the curve. Or it could go the other direction. And that best fit line, we know, if it's a straight line, we know that it will have a slope and a y-intercept, right? Based upon the straight line formula, right? So here's your independent variable. Here's your dependent variable. Here's your y-intercept wherever it crosses the y-axis. And there's your slope. So what do we mean by slope of a line? Slope of a line is rise over run. So if the point is right here, and there's another point right here, then we can calculate what's the distance between this one and that one in the y-axis, and what's the distance between this one and this one in the x-axis, right? Delta y divided by delta x. And if you can see those on the graph, then you can calculate the slope. That's the slope of the line. Now the slope, if it's this way, like that, if it's a direct relationship, in other words, as this one goes up, that one goes up. So from here to here, if this one goes up, that one's going up. That's a positive slope. And the m will have a positive value. If it's the other way, if it goes this way, then as this one gets bigger, that one gets smaller. That's a negative slope. Okay? All right. So we've got the slope of the line. How do you find the y-intercept? Once you've got the slope of the line, then you just pick two values on your graph, preferably ones that are actually touching the line. Plug those numbers in, the x value, the y value, the slope value. Solve for your y-intercept. Or you can actually cross the y-axis and see where it is. Either way. Then you have a formula for that line. And the value of a formula is that you can do what ifs all day long. Say, what if I had chosen this value instead of any of those? Solve it and find out what the volume would be, what the expected volume would be inside, if it's inside those values. Right? That's where we get to the concept of interpolation. If you pick values in here within the measured range that you didn't actually measure, but they're on that line, then you're interpolating. If, however, that's as far as you went here, that's as far as you went there, and you extend that down, extend this up, and you pick some value up here or down here, that's extrapolating. Interpolation is reasonably safe for giving you numbers that you can rely upon. Extrapolation is risky because you don't know what's happening beyond that last point. It could be going this way, it could be going that way, or this way, or that way. You just don't know. So you have to specify if you're going to publish your work and you extrapolate, you better be pretty sure that you need to do that. Otherwise, the reviewers are going to hammer you and you may not even get your paper published. And while I'm on the topic, if you're publishing a graph, you're trying to convey information to your reader. And as a consequence, your graph needs to be self-sufficient. It needs to stand alone, which means you've got to put all this information in there on the graph so the reader knows what they're looking at. And then also it needs a title. So you're saying this is what this graph represents, right? Sometimes we say the effect of something on something else. So in this case, it'd be the effect on temperature on the volume of a gas. So you need the title, you need to lay out your grid, the units, and what they represent, right? The value, what's the variable, what are the units? Then place your points, draw a best fit curve. And then if you need to, you can always put an explanatory note in the graph. But that graph has to stand alone. If I take that graph out, I ought to be able to say, this is what it means. Right? So if we're missing information that I've given you, then the graph is not complete. Okay. Excuse me. Okay, we've plotted data points. We've drawn a best fit curve. Tilting a graph simply means portrait or landscape. Oh, no, titling, excuse me. Titling the graph. Give it a title. I thought tilting. Tilting the graph is portrait or landscape. Here's the discussion of interpolation versus extrapolation, calculating the slope, right? Direct proportion means that way, positive slope. Inverse proportion is this way, negative slope. Okay, and there's how you calculate your slope. And when we calculate the slope of a line, we go from left to right on the independent variable, and then we say what happens to the dependent variable. So this one will be, and you always go final minus initial. So if we're going left to right, the final is here minus the initial. Okay, that's the delta y. If it's negative, then final would be down here minus the initial, which is up here. That's why it's negative, because the final is a smaller number than the initial. That makes the whole value negative. Okay, let's see. There's a discussion of inverse proportionality, and they give you a chemical equation here, which you don't need to worry about right now. We're gonna flesh those out later. But it's just to illustrate that. Let's see. Okay, here's a good graph. Pressure versus volume of a gas. So as we increase the pressure on the gas, what happens to the volume? It gets less, right? So we increase the pressure from left to right, and the volume is decreasing. But it doesn't decrease in a linear fashion. It decreases in a curve, right? We're going to talk about that more when we get to gases and the gas laws. This represents a gas law called Boyle's law. And it simply means that as we increase the pressure, the volume gets less, and it's on a curve. This is a special curve. You may have studied this in math class. It's called a hyperbola, right? The hyperbola, and in math class, the hyperbola has another. It would have one up here, and then it would have another one down here, or it would have here or here. They always have a mirror image. We only use the positive image. So this is our hyperbola. The other characteristic that a hyperbola has, besides having a negative slope, at any point on this line, the tangent to that line, everybody know what a tangent is? It's a straight line that touches the curve. Anywhere that straight line touches the curve, and it changes as we go the curve, then the slope of that line is negative. So that's why we say this slope is negative. What we mean is the instantaneous slope of the straight line tangent to the curve at any point is true for this curve. Also is true is this tail here goes on forever and never touches the x-axis. Or it goes on forever this direction and never touches the y-axis. Ever. Never, ever, never. That's the nature of a hyperbola. Okay. In this case, we've reported the data here. So which one does the experimenter control? The pressure. The experimenter controls the pressure, and the response of the gas is the volume. So this is the x-axis data, this is the y-axis data. And those are the numbers that we plot. 0.25, 96.9, 0.5, 48.4. And those values are plotted here on this curve, and we try to draw the best fit curve. Now, how do you do that with a curve if you're doing it by hand? There's a special device. Have you ever heard of the French curve? It's like a ruler, only it's curved. And it has a decreasing radius curve. So it'll look something like this. Right? So this is a big radius here. This is a small radius here. And you can move that curve around and figure a best fit line to draw for those values. And they're usually transparent because you want to have your points equally distributed on either side of the line. Right? You want to minimize the deviation. So that's what we would do for this one if you weren't using a computer program, and it would draw one for you. So what we see in this graph is a transformation, right? The data as collected is pressure versus volume. But what we don't like curves. Scientists don't like curves unless we absolutely have to use them. We prefer straight lines. So what you'll see very often in the sciences is that data will be transformed to create a straight line. And in this case, we've taken the data, and if we take the inverse of volume here and plot pressure versus the inverse of volume on the y-axis, we get a straight line. Let's see. I'm going to erase this so I can talk some more here. I'll show you why that works. And you'll see this again when we get to the gas laws. This is Boyle's law. P times V equals a constant. Pressure times volume equals a constant. Whenever you see two variables in a product equal to a constant, that's an inverse proportion. Here's why. That is constant. If this one goes up, that one has to go down in order to retain the constant value. Okay, so that's why it's an inverse proportion and a negative slope. Well, if we want to convert this into a straight line formula, what if we divide both sides of the curve by volume? So I'm going to take volume over here, volume over here. We can do that. That's kosher in math. Do the same thing to both sides of the equation. You haven't changed it. So now the volumes cancel on this side, and we've got them on that side. This is K over V. Well, I want to use another math trick and split the volume out. So this means that K in the numerator times 1 over V, keeping the V in the denominator. That's allowed. So now we have, this is our Y value, K is our slope, and 1 over V is our X value. Okay, that's our straight line. Oh, by the way, what's the y-intercept? It goes through the origin, right? See there? Goes straight through the origin. So now if we plot x as 1 over v and y as p, like we did here, we get a straight line. And the straight line is that k value. Now, it's not the same slope as this one would be for any one of the tangents. It's a different slope. We're using different units of measure, so it's a different slope. But it is very useful because we can plot a straight line much more effectively, and we can calculate a formula for that straight line also. Now, one other thing you need to notice is we have, what does this axis represent? It's pressure. What are the units of measure? Atmospheres. With this one, the volume was represented here with units of measure of liters. Okay? When we take the inverse of the volume, we also take the inverse of the units. So here, this axis represents 1 over volume, or the inverse of volume, and the units are the inverse of liters. That's why liters to the -1. That's the math equivalent of the inverse of a unit. Liters to the -1 would be the inverse of liters. Okay? Now, let me let that cat in. Hello. Go ahead. Okay. After saying all of that, this requires a different title, right? Because we've changed the units. We're still working off the same data set, right? Pressure and volume, but we've transformed one of those units so that we can plot it and call it straight line. And notice that the slopes switched. When we took the inverse of volume, now the slope is positive. The other point I want to make is that whoever drew this graph made a glaring error. See these values, 0.25, 0.5, 0.75? Those numbers possess what I call orphaned decimals. When you have a decimal sticking out here by itself, it's orphaned. It needs both parents. That is, it needs a 0 on the left-hand side. Right? If I see that on anywhere, on a graph, on the answer to any question, doesn't matter, I will count it wrong. I know some teachers in the public schools do it that way, but respectfully, they are wrong. You need that 0 to bracket in that decimal point. Okay. So this is another set of data that's got a negative slope. In this case, the curve is not a hyperbola. Notice, because it intersects the y-axis. I'm not going to spend a lot of time on this one. It can be transformed, right? In this case, we transformed it with logarithms, right? We took the log of this y value, and that gave us a straight line. So we're not going to go into that much detail. So you don't have to worry about this one. Let's see. Okay, from now on, this discussions from now on, in fact, including this one as well, are part of this exercise is required. And let's see. This part is required, and it's worth 78 points. This particular exercise is not a formal report. This is an informal report, which means you just do the work and fill in the answers and submit the hard copy. The reason I'm doing that is because I want to give you time to get your lab notebook set up and get the feel for experimenting and doing this stuff before you actually have to write a formal report. So this is going to be, let's see, this is an informal report, and I think the second one is also. Yeah, the second one is laboratory techniques, where we actually go in the lab and we just use various techniques to get familiar with them. That's an informal report also. The third experiment is where we start with the formal reports. And I've given you, well, actually, yeah, I did hand them out. I did give you information on writing a formal report. I gave you a sample report that you could work off of, you could imitate. And I gave you the rubric that I'm going to use to grade so you know what I'm looking for. And then we can talk about it more later. But when we go into the lab for the lab techniques, we're going to be working off of a hard copy document. That's in a couple of weeks. So you'll need your lab coat and eye protection. And I would encourage you to study the lab before you go in. And since we're on that topic, I'll say the first line of defense against accidents in the lab is know what you're going to do before you go in. Be familiar with the lab. Don't just cookbook it. Say, walk in there, open the page and say, oh, this is what I'm doing today. Oh boy. Let's go have an accident. Know what you're going to do before you walk in. For the informal labs, it's just a matter of reading the lab and asking yourself questions. What would I do in the case of emergencies? Where are the hazards located? In the formal labs, I'm going to require that you set up your notebook with information from the hard copy so that you can take your notebook and do the lab, and the hard copy stays in your purse or in your briefcase. Or you can leave it at home, I don't care. But your lab notebook is what you work from. So you need to set up your lab notebook in such a way that you can do the entire lab from the notebook. So it's up to you how much information you put in there. You want to put in there enough so that you can do the lab, right? As much detail as you need. When I set up my lab notebooks as an employee of the government, I would put in nauseating details because I wanted to be able to come back 6 months later and repeat the experiment if necessary and know exactly what I did to conduct that experiment. If you're very vague, then you may do it the same way and you may not. Okay, so this section is the required section, and we start off by just answering questions, and you can extract those from the introduction to the lab. And then, let's see, answer more questions. Let's see. And then we actually get to the point where we're going to plot data. Here's your data, right? A study was made of the effective temperature on the volume of helium gas. That's a good title. So the effect of is the independent variable. The temperature is what you control as the experimenter. And the effect of on the volume. The volume is the response. The volume is the y-axis. Okay? And this one right here, worth 10 points, is where you plot the graph. So you need graph paper, right? There's graph paper in the hard copy of Method. If you find that you need some more when you come to class on Thursday, I'll have graph paper with me so I can give you some extra sheets in case you make a mistake and you have to start over again. So you'd plot that one and then you'd answer questions about it. Here, at what volume would the helium sample have a temperature of 5 degrees? Well, look up here at 5. Is there a 5 degrees there? No, there's not. So you plot the graph, you draw your best fit line, and then you go to 5 degrees on the x-axis, follow it over to the y-axis off that line, and that's the volume. That's what you record right here. Okay? And don't forget your units, right? The question is asking for volume, so what would the units be? Liters, right? Don't leave the liters off, otherwise I have to count points off, and that takes a lot longer to grade. Perfect papers are easy to grade. You just check, 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 check. Papers that have mistakes take a long time to grade because I got to correct your mistakes and tell you where you went wrong, and it's a learning experience. At what temperature would the helium sample have a volume of 4.20? Now we go the other direction. We go up the y-axis to a volume, follow it across to the line, go down to the x-axis. That's your temperature in degrees Celsius. This one actually tells you to calculate the slope of the line. So how do you calculate the slope of the line? You need 2 data points, right? The y values from those 2 data points, subtract them, and put that in the numerator. Then you subtract the 2 data points x values, put those in the denominator, calculate the slope. Now, what are the units of the slope? Let's see. We've got sometimes it helps to draw a picture. Okay, if you've got this graph here, and actually you're going to need some negatives, aren't you? Right? You're going to need some negative x's. So we'll extend it out this way. And your best fit line is going to be like that. Probably, right? Isn't it? As we get bigger temperature, we get bigger volume. Yeah, so it's going to be a positive slope. Once you calculate your slope, like you've got 2 points here, and you go like this and this. So this delta, this is delta x, and this is delta y. No, this is delta x. This is delta y. There we go. So it's for the x-axis, it's this one minus that one. For the y-axis, it's this one minus that one. Gives us a positive slope. So once you've calculated the slope, what are the units of measure for the slope? We're looking at it this way. If it's delta y over delta x, and y is volume, and x is degrees C, there's your units. Liters per degree C are the units of your slope. Then calculate the y-intercept. I mentioned that earlier, but I'll tell you again. Once you have the slope, right, you have the slope here, like that, and that's times x, and this is y, and you have your y-intercept, we want to know that value right there. So you can either read it off the graph, or you can calculate it. I would suggest calculating it because you're going to have to report the equation anyway, right? That's part of the answer. Y-intercept and equation. So you calculate the y-intercept. You say, we've got, when you draw your line, hopefully you will have one of these on the line that will fall on the line. So you pick one. Let's say, I don't know, 6.53 would be volume, would be Y, 6.53. And X would be 50, 50 there. And then you have some value here, right? There's your unknown right there. All right. So you multiply these together, you subtract them from both sides. So there would be this one minus this product. That's equal to your y-intercept. You report your y-intercept. And then um, when you do the line equation, you have two choices. And I don't care which one is which. You could say y equals mx plus b, and you just put the slope value and the y-intercept value there and say y equals something times x plus something. Or you can say, excuse me, volume equals something here times temperature, right? Temperature plus something there. That's okay too. Okay, here's another graph, and we've drawn one just like this, right? So this one should be easy. Pressure volume relationship of a gas. And it should look like that curve, right? What you want to do is choose your values of we're changing the pressure. That's the experimenter. So that goes the x-axis. Volume is the y-axis. So we want to go on the x-axis up to, say, 4, right? 4, nice round, even number. 4 atmospheres on your x-axis. Use the entire stretch. And on the y-axis, we want volume in liters. The volume in liters is going to go from 14 to, say, 100. So that should be okay to go from 0 to 100. You should be able to get that on the y-axis. Now, which one should it be, portrait or landscape? Which one needs the most room? 0 to 100 or 0 to 4? 0 to 4 should be the shortest one. So that means it's portrait, right? And the volume is the Y, so it needs the more room. So you would draw that one as a portrait. Okay, and that's what we're doing right here. Tell me, is this a direct relationship or is it is there a direct relationship? Right? Remember, direct relationship says as x increases, y increases. What did the P times V look like before? As x increases, y decreases. That's an inverse proportion or an inverse relationship. Let's see. Then we got another one here where we want to transform that data and draw a linear graph of it. So we would take the inverse of these values and plot them against each of the x values. Okay? So you're going to have 3 graphs minimum, right? You're going to have volume temperature, you're going to have pressure volume, and you're going to have pressure inverse volume. 3 graphs minimum for the required section. Then there's a bonus section. And if you feel brave, you can get in there and earn some more points. So you have the potential of making more than 100% on this lab. Let's see. I will say this. I think the second, oh, there's your graph paper. There are two graphs in this one. There's a graph and based on this data, and this graph is based on that data. This is a titration curve, and we don't do that one until the second semester. But I'll show you what it's supposed to look like. Oh, let's see. That's my time. Oh, 350. Okay, good, good. If we plot, okay, what we're doing is we're adding base, sodium hydroxide, to an acid, and we're measuring the pH. That is a measurement of acidity of the solution. So you really don't have to understand what's going on as long as you know which one's which. So we're adding the sodium hydroxide, which means that's the independent variable. That goes on this axis. This is sodium hydroxide in milliliters. Yes, milliliters. And on this one is the response, or the pH. Okay? The pH doesn't need an explanation. pH is it, just pH. That's one exception to having the axis identified and then the units of measure. That axis identity is the unit of measure. So you just have to say pH. And what we get is acid is a low pH, and we add base, and it gradually starts coming up and then it flattens out. And then it goes to a point, and then it goes to equivalence here, and then it goes out like that. It's a sigmoid curve. Now, this point right here represents the volume at which the pH reaches equivalence. And what that means is the amount of acid exactly equals the amount of base, the amount of sodium hydroxide. That's what that means. Let's see. So if you plot the data, it should look like that. Sigmoid curves are, this is the only one I know of in chemistry. There are probably others, but I've seen them a lot in biology. The sigmoid growth curve of a population of bacteria, of insects, of larger animals, the sigmoid curve. So you start off at this level, and then the food supply, the reproductive rate is kind of slow at first, and then it just goes boom. And the reproductive rate increases the population until they exhaust their food supply and then levels off. And sometimes it crashes on the other side. But the sigmoid curve is, you'll see it lots of places. This other set of data here, this is what I call a broken curve. So if you figure out which is which, right, you're changing the temperature, right? A study of reaction of hydrochloric acid and ammonia, a student collected the following temperature data. So over time, as you mix them together, you're measuring the time, and the temperature is the response. So temperature is on the y-axis. And this is time. In seconds, I think. No, minutes, excuse me. Okay, so what you get is the as the time increases, and it looks like it increases in 1 minute intervals, half-minute intervals to begin with, and then that changes to 1 minute. And this point right here is when you mix. That's when you mix the two ingredients. So your temperature is doing something like this, then you mix it and it goes up here like that. That's what I call a broken curve. Now, if you need to draw some conclusions between this part of the curve and that part of the curve, and they don't overlap here, like that, they don't overlap. So what you have to do is extrapolate this one, extrapolate that one, and then say, there's the difference in temperature. Okay, that's why I made those bonus, because it's kind of, yes, it's a little beyond first year chemistry. But if you're game, you can answer some of these questions and maybe pick up a few points. But the rest of these are required. Let me see if I've forgotten anything or if you have any questions. All right. There's a lot of introductory material here. Yeah. Um, okay. Oops, I didn't mean to do that, but I guess that's all right. So we have choice. We've got a lot of time left. We could go back into the um, review document and finish off those last 10 questions. That way we won't be crunched on Thursday. Um, I don't know what the weather's going to do on Thursday. They say by the weekend, we got another snowstorm coming. So if it leaves us alone till Thursday, we can meet face to face. So you guys think about it for a minute, and I'm going to take another bathroom break, and I'll be right back. All right. So you guys want to finish off the chapter 1 review?
I actually wanted to clarify really quick about
Okay, sure.
um everything we need when turning in a lab. So the lab notebook, can that just be any just notebook
Oh, no,
or
no, no. You'll see in the syllabus, there's a picture of one. You got a copy of the syllabus
okay.
with you?
Yes.
Yeah. Okay. Look in there. There's a picture of one. It's what we call quadrille lined. It's like graph paper.
Okay. Okay.
Every page is like graph paper. And yeah, let's talk about that instead of doing the other thing. Um, So let's see. Do I have a copy of one? No, I don't have one with me. That's what happens when you work from home. Wait a minute. Maybe I do have one. No, no. So this quadriline notebook, I get them at Walmart for like $2.60. And I've got several that if you want, since you've got time, you can buy one from me for $2.60, I think. It was the last one I bought. And we want quadriline paper so that you can draw graphs in your notebook if you need to. Now, when you set up the notebook, there's basic information that I want to see the first time I check it. And if you look in your schedule, you'll see, let's see, no, the schedule for 103, excuse me. The schedule, your 103 lab, the first lab notebook check is on the 10th. Yeah, on the 10th. That's the day we go into the lab for our lab techniques. And that's the day that the graphing techniques is due. Okay. So what all I want to see that on that first setup for your notebook is either on the if it's some of these notebooks you can't write on very easily, even with a Sharpie. So you may have to write on the inside cover. But I want to see your name. I want to see the course, prefix, and number. Right. So that'd be like CHEM103. And then the semester. Okay. Like spring 2026. That will be on the front cover or just under the cover wherever you can write on it. Some of these have such a slick surface on them, and they have to be bound. I don't want any loose leaves. They have to be sewn together. Okay. The next thing you do is you go in and you take the notebook, and the first page is going to be on the right-hand side. Right. And that one gets a number 1. And you flip the page over. On the left-hand side is number 2. And the right-hand side is number 3. In ink. Any color you want except red. And I want you to number every page from the front to the back. So that means all the right-hand facing pages are going to be odd numbers. And all the left-hand facing pages are going to be even numbers. So when if you're going along and you're distracted and you notice you're starting to put even numbers on the right-hand side, odd numbers on the left-hand side, stop. Go back and find out where you made the mistake. And just number all the pages to the end. And then on the first page, page number 1, just write at the top, table of contents. That's all you have to do. That's what I want to see on the first notebook check. Listed in your syllabus on the 10th of February. Then the next time we go in the lab on the 24th of February, that's going to be your first formal lab. So at that point, I'll give you a handout at least a week before for the exercise. You take the exercise and On the table of contents page, you say this will be exercise. So it'll actually be exercise number 3. So you could say number 3, and you put the title, which would be Waters of Constitution and Hydration. Title, and then the page that it starts on. That's all you need. Page that it starts on. So you can flip the page over and start on page number 3, or you can flip a couple of pages, start on page number 5. Let's say you do that. You're going to start on page number 5. And I want you to write when you're filling this out and getting ready, only write on the odd pages on the right-hand side. Leave the left-hand side alone. There's a reason for that. You can draw a graph over there, or if you make a huge mistake on the right-hand side and there's no room to make the correction on that page, then you can cross through that one and draw an arrow to the left-hand side and write what you wanted to write on the left-hand side. It gives you a place to put it. That being said, the best way to set up your lab notebook and put information in is make big gaps between your lines. So if you write out your method and you're writing step 1 here, skip 2 lines. And that way you can make small corrections without scrunching things together. Okay, so setting up your notebook, I should have had a handout for that. What do I want to see when you walk in the lab to do a lab exercise? What do I want in your notebook? Right, there should have been a handout for that. So on this page 5, you're going to have a title at the top. Then you're going to write a blurb with a heading. Put your headings in recognizable text and maybe underline them. It's going to be an introduction. Introduction. Then you're going to write something. Then you want to say something about safety. You know, what are the hazards that you have to watch out for? Like an open flame or a hot plate or glassware that might break, or if we have any hazardous chemicals, right? Then you want to put that in here as safety concerns, right? Then the next section, you want materials, right? And you'll have a list. You can do a bulleted list, something where you can identify what is actually going to be used to do the experiment. That includes chemicals, equipment, any other consumables like filter paper, thermometers, anything that's going to be used. You can extract that from the procedure, from the document that I give you. Now, sometimes these methods will have this well organized, and sometimes they won't. So you may have to dig for some of this information, but this is where you want it to be. So now you know what materials you're going to gather, or like an analytical balance, right? You're going to weigh some things out, so you need the balance. Then next, you want the procedure. And you want to go step by step. You're telling yourself what to do next. Do this, do this, do this as instructions, right? So it may say weigh to 3 decimal points the sample of sodium chloride of 1 gram, right? So you weigh it on the analytical balance, and you weigh 1 gram, and you want to use all the decimal points that you have available. So if it's an analytical balance in our lab, it'll have 4 decimal places. So 1.0045 grams, whatever the value is. Right? So you're telling yourself what to do at each step. That's the procedure. So far, you've actually had to write some things in your notebook. Right? Next, you want a place to put your data. Right? So you set up you have a heading, data, and then you leave space for your data. Now, what I suggest is, depending on the type of data you're going to collect, you may need a little bit of room, you may need a lot of room. So you look at the procedure and say, how much room am I going to need? Am I going to need a whole page or just a few lines? And if you can, go in and identify the data that you're going to need. Right? So if you're going to collect data, then you want a place to put it. So I would say, this is that data, and here's where it goes. And if you know the units, say it's going to be in grams, write them in. So you have that blank, and you know there's supposed to be something that goes there when you do the experiment. If there's going to be a lot of data, you may have set up for a list, or you may set up a table, right? It just depends on the experiment. And then you'll have other things, and these are in order of the procedure, right? This one may be milliliters. This one may be pH. Who knows? But you have identified what goes in that spot. The reason that I want you to do that is because you're going along, you're doing the experiment, and you're down here putting in numbers, but these are blank. Why are they blank? Did you miss a step? Right? If you see that blank up there, stop and say, all right, is there supposed to be something in there, or did we skip it on purpose? If you skip it on purpose, just go in here and go like that and initial it. Anytime you make a correction, initial it. Right? It validates it that you, as the experimenter, did it. If somebody else uses your notebook, right, and that can happen in companies or government labs, you have your notebook set up and you're absent one day, and they go ahead and carry out the experiment for you. Then if they make a correction, they initial it with their initials, and we know who's responsible for that correction. If you just have a very small corrections, you can draw a small X or a line through it and initial it. If you have big corrections, you can draw a big X through it and then a big signature. Okay, so now you have a place for your data. You're not going to have any numbers yet. You're not going to have any observations yet because you haven't done the experiment. And then you're going to need a space probably for calculations. That's another heading, and leave space for your calculations. Sometimes you can put things in here that you're going to end up calculating. Sometimes you can't, so it's okay to leave this one entirely blank. Just leave yourself enough room for the calculations. And then many of these labs have questions. And you can put them anywhere. There might be pre-lab questions. If you have questions that are identified as pre-lab, right? Pre-lab questions, you can stick them in down here, or you can stick them in after the procedure, right? Those need to be answered before you come in the lab. They're pre-lab for a reason. They're giving you experience. They're trying to tweak your mind to get in the right frame of mind for the experiment. So some of them will have just plain answers, straight answers. Some of them will have explanations. Some of them will require calculations. And then very often at the end of the lab, there will be post-lab questions or just called questions. And they can go at the end. After calculations, you can do questions. Those questions, there won't be any answers for those, right? Not until you've done the lab. And some of these questions involve actually doing calculations on the data that's involved. And if that's the case, if a calculation is required for a question, you've already done the calculation in this section, you can just refer to the calculation section and say, this is my first, second, third, fourth, say the fifth calculation answers that question. And that's good enough. There's no sense in you writing it twice. So you answer these questions, and then at the very end, we want a summary and conclusions. Summary is just a short paragraph of what was done and what was discovered. And then the conclusion is, what does it mean? And if you set your notebook up this way, and then you fill in all the information as you do the experiment, and then do the calculations and answer the questions, when it comes time to write the formal report, it'll be a piece of cake because it's all right there in front of you in your lab notebook. You just transpose it into a readable form in a formal report. The only difference between your lab notebook and the formal report is the procedure. The procedure tells you what to do, and you make corrections. If there are any changes in the procedure, you make corrections in your notebook. Say, this is what we actually did. Because when you write the report is going to be in the passive past tense, which means this is what we did. This tells you what to do. The report says this is what we did. There's a distinct difference between those two. So if the procedure says measure 150 milliliters of water using a graduated cylinder, in the report you would say 150 milliliters of water was measured using a graduated cylinder. Okay, that's the difference. Some students never get it. They just, I don't know if they just freeze, or they don't understand what's required, or I wouldn't doubt that some of them are just lazy, or they've bitten off more than they can chew. Right? They've taken too many courses. They don't have time to be bothered with a formal report. So their formal reports are essentially garbage. Okay, so that's what so the first time we go in the lab for lab 3 on the 24th of February, your notebook should be set up that way. For the 10th of February, it'll be set up just with the bare bones. Okay, and if you need a copy, if you need a lab notebook and you can't find one because they run out of them at Walmart, if you can't find one, then I can sell you one at class on Thursday. Yeah, I'm not making a profit. I'll sell you one at cost. Okay. So we've still got a few more minutes. Anybody have any questions? And I don't know if I handed out a sample, like a photo copy of parts of a lab notebook to show you what it looks like. If I didn't, then go to Brightspace and you'll find one there in Chem 103 Brightspace course. There should be a sample notebook to show you what it looks like. And we'll do that for each of the labs. Let's see. Yeah. 3, 4, 5, 6, and 7. The third through the seventh lab are all formal reports. And then at the end, I'll do a final lab notebook check on the 12th of May or earlier if you have your notebook completed. And you can make corrections in your notebook. It doesn't have to be pretty. I know some of my students want their notebooks to be just showpieces. It's like put them in a frame and hang them on the wall. Lab notebooks are not intended to be that. You want them to be legible, of course, because if you work for a company or the government, when you work that lab notebook and you're lab tech, then if you leave the company or leave the government, that notebook stays behind. It belongs to the company. So you want it to be readable, so legible. So do take time to use reasonable penmanship. Um, but it doesn't have to be pretty because things change. Once you set it up and you go in the lab, things can change. Like maybe I've discovered that we've run out of a certain reagent and we have to substitute a reagent for it. And you'll make that change in your notebook so that when you write your report, you can say what actually was done. Okay, that's probably enough for now, and you'll have questions later.